Now we will discuss very important property of manifold and how we can distinguish them. We say that by definition the manifold is locally look like as Euclidean of the same order. That means if I have two manifold locally look like exactly the same, and I cannot distinguish between them, so I cannot classify. So how could I classify them? I need to introduce the global consideration, the global structure of the manifold. So by considering the global structure of the manifold, this manifold could be classified according to this global structure. And here there is very funny two examples. The first is a ball with a cube, but a cube without handing, without this a way to hand it. So these two the both are manifold, and locally each one, if I look locally, they are exactly the same. And the same, for example, if I take torus with teacup have handing this handing stuff that help me to hang the teacup. So the both has just one hole, but locally at each point they are, since they are manifold, locally look like exactly the same. But here I need to consider very important properties, that the cube shouldn't have this very sharp end. I mean, should be have smooth end everywhere. So in order to be considered as exactly the same. So smooth is also important to take into consideration, because differentiability. I need to ensure the differentiability property. So the two manifold, each previous example had the global structure, different global structure, so I can classify them. And here is amazing properties also. As I say, I need to parameterize any manifold. I need chart, which is, for example, at least two chart for a ball or for a sphere, as we discussed previously. So here there's important properties that there is mapping between these two structure, equivalent structure, globally equivalent structure. For example, a ball and this cube, or torus and T cube. So there is mapping between them, which is called diffeomorphism. Diffeomorphism, that means continuously I can differ a ball continuously without touching any of its differentiable properties or topological properties until I get this cube. And the same for torus. There is a kind of diffeomorphism between them. This and if there is such diffeomorphism, then I call them are diffeomorphic to each other with respect to each other, to one another. So this is fun. This is another remark should be mentioned. In most cases, I don't care about the global structure, so I just care about locally. But in some cases, very important, fiber bundle, integration of function, the global properties should be taken into consideration. And we will see, for example, for what Möbius structure, that this global structure is important. The global structure usually is not important, but in some cases is important. Finally, there is very important definition which is called curve. Curve of manifold is series of points, not only series. There is condition that there should be continuous series. That means there is differentiability, differentiable mapping. So this series could be parameterized in R1. So this is the curve. So any series, any continuous series of a manifold could be parameterized in R1 called a curve. So there is mapping, differentiable mapping from R to M to this manifold, or the opposite, it's equivalent. By another word, another equivalent definition, the coordinate of the image point, sorry, the both definitions are equivalent. Either I take continuous series of points from manifold, or there is kind of differentiable mapping from R to R1 to M. So this is what they call the both definitions are equivalent. Finally, what I call by differentiable mapping, that means the parameter or the coordinate in R1 are differentiable function. So of lambda. So the coordinate of the image point are differentiable function of lambda. So this is a curve is very important definition for in manifold. So next we will have a look for function on manifold, and also vector field soon.